Okay, let's go ahead and get into our next topic. It's 16.5, strong acids and bases. So beginning this, just want to make sure that you have a reminder of which acids are strong. We have 7 common ones, and we have a mnemonic device we have here, which is so, no, close, and brickle. So no, close, brickle. The idea behind that is it's just designed to help you remember what all of the anions are that we're using in these strong acids. We have the SO, representative here of our sulfuric acid H2SO4, NO for nitric acid HNO3, our close ClO, that's chloric and perchloric acid HClO3, HClO4. And then we have the brickle, which is hydrobromic, hydroiodic, and hydrochloric acids. Now, indicative of the typical behavior of these acids, we have nitric acid, which is going to separate into its hydrogen ion and nitrate ion. Now, one of the nice things that we have, what's very convenient for us, is we don't actually have an equilibrium arrow. What happens in the case of strong acids is they will completely dissociate. Okay, so they completely separate into their ions. The molarity of any of these acids, so let's say you have a 1 molar acid, well, that tells you if it was 1 molar initially here, there's a 1-to-1 ratio of the hydrogen ion to the molecular acid. So in a 1-to-1 ratio, that means starting with a 1 molar nitric acid solution, it would separate to make 1 molar hydrogen ion. And it's really easy for us to figure out things like pH based upon that information. Now, just to verify you're getting this concept, I want you to do this check for understanding here. So first, what is the concentration of hydrogen ions in a 0.2 molar nitric acid solution? Thought about this. Remember, as nitric acid breaks down, it's monoprotic. There's only one proton here. So that means that for every 1 nitric acid molecule, 1 hydrogen ion separates off. If we begin with 0.20 molar HNO3, we would say it must be 0.20 moles per liter of solution as the beginning. Well, we can do a mole ratio to convert out of every 1 mole of the nitric acid molecule produces 1 mole of hydrogen ions. That tells us that the starting concentration of the acid has to be the same as the ending concentration of our hydrogen ion. Okay? Now, I want you to also consider this second concept. If we were to have sulfuric acid, this time around, it's diprotic. There are 2 hydrogen ions that separate off from our original sulfuric acid molecule. What we're going to have to do with this is then think, well, if the beginning was a 0.060 mole H2SO4 for every 1 liter, I can use the mole ratio here as well. 1 mole of the sulfuric acid would produce 2 moles of hydrogen ions. So, considering that, what we have to do is essentially double the initial molarity. So my 0.06 becomes 0.120 molar hydrogen ion concentration. Now that we've done that, let's talk about our strong bases. So very similar to the strong acids, the strong bases are going to completely dissociate into ions also. Now, in short, we have all of the hydroxides of alkali metals. So that's lithium, sodium, potassium, rubidium, and cesium. All of these are going to completely dissociate in water. Then we also have the alkaline earth metals that are a little bit heavier. So that's the calcium hydroxide, barium hydroxide, and strontium hydroxide. Those compounds will also completely dissociate. One thing to pay attention to is that with the calcium, barium, and strontium, these are sparingly soluble. So what does dissolve in water? is going to fully separate. However, if you have a solid sample, a very large amount of solid, not all of that solid is going to dissolve. So, as we did before, we're going to think about this. The initial concentration of our combined molecule will fully separate, and the molarity of that starting base would be the same as the molarity of hydroxide ions that come out. Here we have potassium hydroxide. Since it begins as 0.0080 moles per liter KOH, that is going to directly go in a 1-to-1 ratio to 0.0080 molarity of hydroxide ions that come out. So it's important that you get that concept as well. For something like calcium hydroxide, pay attention to the number of hydroxide ions here. Well, that calcium hydroxide is going to split into not 1, but 2 hydroxide ions when we write out that dissociation equation. That means, just as before, we're going to have to double the concentration. I began with 0.30 molar calcium hydroxide, and that is going to turn into 0.60 molar hydroxide ion. Now that we've got that, let's think about this. It'll give it some thought. Which solution has the higher pH? A 0.001 molar solution of sodium hydroxide or a 0.001 molar solution of barium hydroxide? So you've got to remember, this has only 1 hydroxide in its formula. The barium has 2 hydroxides. What this means is that the barium hydroxide is going to be more basic. It's going to have more hydroxide ions present if they begin with the same molecule molarity. That means barium hydroxide will have the higher pH as well. So, side note once again, we don't commonly use lithium, rubidium, or cesium hydroxide in the lab just due to cost and availability of some of these compounds. Also, when we're going to be studying some of the alkaline earth metal hydroxides, it is important that we pay attention to the fact that these things are only sparingly soluble. So if we're going to have a situation where precipitates could form, we just have to keep in mind that that is something that can happen. We may not want to use those in certain cases. Something else that you might find is in a practical setting, in industrial processes, we would use metal oxides such as sodium or potassium hydroxide, sodium or potassium oxide to make some strong bases based on the way that they can interact with water molecules. So in sodium oxide, remember that this splits off into 2 sodium ions that will act as spectators, and it would also form an oxide ion. The oxide ion will then interact with water to make 2 hydroxide ions. That's going to be our strong base that results once an oxide is put in water. So, final check for understanding based on these. I want you to think about, once again, all about the ratios. You've got calcium oxide. That's going to split into calcium and oxide ions. If you have a 0.070 molar calcium oxide, follow-up reaction of oxide and water is going to make 2 hydroxide ions. So if the goal is to figure out hydroxide ion concentration here, we would know that 0.070 moles of our oxide ion that come out here can be converted in a mole ratio. It's going to be 1 mole of oxide here for every 2 moles of hydroxide. So 1 mole of oxide, 2 moles of hydroxide forming. Putting that together, we have to double that initial concentration to become 0.140 molar hydroxide that would come out. The second example now, we're asking what's a concentration of hydroxide that would be formed from a 0.80 molar K2O solution. Now, in this case, remember, K2O, it's going to form 1 oxide from this initial molecule. So we'll set it up just as before. This time it's 0.80 moles of the oxide per liter. We're going to put this in our 1:2 ratio. 1 mole of oxide ions for every 2 moles of hydroxide ions formed. So we'll end up doubling this to get 1.60 moles per liter of our hydroxide ions. Now, consider this next give it some thought problem. The CH3- ion is the conjugate base of CH4. So CH4 methane shows no evidence of being an acid in water. So, right, no evidence, it is a negligible acid. Write out a balanced equation for the reaction of CH3- and water. So this balanced equation, as we think about it, it's CH3- with H2O. So it shows no evidence of being an acid in water, so it won't donate hydrogen. Instead, it would act like a base in water, meaning it has to gain the hydrogen. So H2O donates a hydrogen that'll act as an acid. We're going to form CH4 and be left with hydroxide ions.